Welcome back to What Is, the channel where we take the universe's most complicated topics and try to explain them before your coffee gets cold. Today we're tackling a big one, the heavyweight champion of wait, what did he just say? The subject that makes geniuses feel like toddlers, and makes toddlers are actually surprisingly good at this because they don't have preconceived notions about how reality should work. Today we're asking, what is quantum mechanics? Right now, you're sitting there, or standing, or perhaps lying down in a state of existential dread. You see chairs, walls, and screens. They stay where you put them. If you throw a ball, it follows a nice, predictable curve. This is classical physics. This is the world of Isaac Newton, where things make sense. But if you were to shrink down, past the cells, past the molecules, past the atoms, to the subatomic level, the rules of the universe don't just change, they lose their minds. At its core, quantum mechanics is the branch of physics that describes the behavior of matter and energy on the scale of atoms and subatomic particles. And let me give you fair warning. If you aren't confused by the end of this, you probably weren't listening, or you've ascended to a higher plane of existence. Even Richard Feynman, one of the greatest physicists to ever live, and a Nobel laureate, famously said, "I think I can safely say that nobody understands quantum mechanics." So with that said, let's take a deep breath. We're diving in. To understand why quantum mechanics exists, we have to look at what it replaced. By the late 1800s, physicists thought they had it all figured out. They had Newton for gravity and motion, and Maxwell for electromagnetism. They were basically ready to pack up their labs and go home. But there were a few pesky problems. Tiny things they couldn't quite explain. One was black body radiation. According to classical math, a black body, an object that absorbs all light, should radiate infinite energy as it gets hotter. This was called the ultraviolet catastrophe, which sounds kind of like a bad 80s synth pop band. In 1900, a man named Max Planck solved this catastrophe by suggesting something revolutionary. He proposed that energy isn't like a smooth, continuous stream of water. Instead, it comes in tiny, discrete packets. He called these packets quanta. Think of it like this. Classical physics thought that you could buy any amount of energy sand you wanted. Half a grain, a billionth of a grain, whatever. Planck realized that nature only sells energy in pre-packaged bags. This is the quantum in quantum mechanics. It was an act of mathematical desperation, as he put it, but it changed everything. A few years later, Albert Einstein took Planck's idea and ran with it. He used it to explain the photoelectric effect, how light hitting a metal can knock electrons loose. He proved that light, which everyone thought was a wave, also acts like a particle. We call these light particles photons. This leads us to our first major concept, wave-particle duality. Imagine you have a pet that is both cat and a dog at the same time. No, not a hybrid. It's 100% cat and 100% dog. It only decides which one it wants to be depending on how you look at it. This is the double-slit experiment. When physicists fire electrons through two slits at the screen, if they don't watch the electrons act like waves, interfering with each other. But the moment a sensor is placed there to see which slit the electron goes through, the electron decides to act like a particle and just goes through one. The mere act of observation changes the behavior of reality. It's like the universe is a shy teenager who acts totally normally the moment you walk into the room, but was throwing a wild party 2 seconds before. This brings us to the most famous concept, superposition. You've probably heard of Schrödinger's cat. Erwin Schrödinger, a brilliant physicist who probably shouldn't have been allowed near a pet store, created a thought experiment. A cat is in a box with a radioactive source and a vial of poison. If a single atom decays, the poison is released. Because we don't know if the atom has decayed until we look, the cat is mathematically both dead and alive at the same time. Now, Schrödinger actually meant for this to sound ridiculous. He was trying to show how absurd the Copenhagen interpretation of quantum mechanics was. But the joke was on him, because the math actually holds up. Objects at the quantum level exist in a blur of all possible states simultaneously. This state is called superposition. It only collapses into one single reality when an observation, a measurement, is made. But we're not done. It gets weirder. Let's talk about quantum entanglement. Albert Einstein famously called this spooky action at a distance. Imagine you have two magic coins. You flip one in London, and it comes up heads. At the exact same nanosecond, the other coin in Tokyo comes up tails. Every single time. No matter how far apart they are, even if they were on opposite sides of the galaxy, they are linked. In the quantum world, particles can become entangled, meaning the state of one instantly determines the state of the other. It defines our understanding of space and time because the information seems to travel faster than light. Einstein hated this. He spent the rest of his life trying to prove it wrong, and he failed. It's very real. Then there's the uncertainty principle, courtesy of Werner Heisenberg. We have already done a full deep dive on this. Please check it out after this video. Heisenberg, who for the record had nothing to do with blue crystals in New Mexico, realized that there is a fundamental limit on what we can know. You can know exactly where a particle is, but you won't know where it's going. Or you can know exactly where it's going, but you won't know where it is. You can't have both. It's not because our microscopes are not good enough. It's because the universe itself is inherently fuzzy. It's like trying to take a photo of a moving fan. You can get a clear photo of the blades, but the motion is gone. Or you can get a blur of motion, but you lose the location of the blades. Now you might be wondering, who are the people who put us through this headache? The golden age of quantum mechanics happened in the 1920s. You have the Solvay Conference of 1927, which was essentially the Avengers Endgame of physics. You had Einstein, Bohr, Curie, Heisenberg, Planck, and Schrödinger all in one room. The big showdown was between Albert Einstein and Niels Bohr. Einstein was the realist. He believed the moon exists even when you're not looking at it. He famously said, "God does not play dice with the universe." Niels Bohr, the father of the Copenhagen interpretation, supposedly shot back, "Einstein, stop telling God what to do." Bohr argued that there is no real world underneath the quantum one. There is only the world we measure. This debate shaped the 20th century. While Einstein's general relativity gave us a beautiful understanding of the massive, stars, galaxies, gravity, quantum mechanics gave us the small. The problem? They don't talk to each other. They're like two different operating systems. Gravity works on Macs, quantum works on PCs. And so far, no one has found the adapter cable to create a theory of everything. So why does any of this matter? You might think it's just ivory tower nonsense, but you are currently using quantum mechanics to watch this. The silicon chips inside your computer or phone rely on quantum tunneling, the ability of electrons to pass through physical barriers that classical physics says they shouldn't be able to. Without Bohr, Heisenberg, and the rest of the gang, we wouldn't have lasers, MRI machines, LED lights, or the GPS that prevents you from getting lost in your own neighborhood. But what about the big questions? The ones that keep the physicists up at night staring at the ceiling. First, the measurement problem. What counts as an observer? Does it have to be a person? What about a cat? Or a single camera? Or a grain of dust? At what point does the quantum world end and the classical world begin? We still don't really know. Second, the many worlds interpretation. Some physicists, like Hugh Everett, suggest that the cat doesn't actually choose to be dead or alive. Instead, the universe splits. In one universe, you see a dead cat. In another, you see a living one. Every time a quantum event happens, the universe branches. If this is true, there are an infinite number of yous out there, and an infinite number of me as well, including one where I actually understood this script the first time through. And finally, what does the future hold? We are currently living in what many call the second quantum revolution. We're moving from observing these effects to engineering them. Enter quantum computing. A normal computer uses bits, ones and zeros. A quantum computer uses qubits, which can be a 1, a 0, or both at the same time thanks to superposition. This would allow computers to solve problems in seconds that it would take today's fastest supercomputers billions of years. We're talking about simulating new medicines, cracking any encryption on the planet, and optimizing everything from global traffic to climate models. We're also looking at quantum cryptography, using entanglement to create unhackable communication lines, because if someone tries to eavesdrop on a quantum message, they are observing it, which collapses the state and alerts the sender. It's a built-in alarm system from the laws of physics. So what have we learned? Quantum mechanics is weird. It's counterintuitive. It's frustrating. It suggests that the deepest level, reality is a ghost show of probabilities and spooky connections. But it's also the most successful scientific theory in human history. It has never once been proved wrong by an experiment. We live in a world built on a foundation we barely understand. We are like sailors on a vast, shimmering ocean, learning to navigate the waves while still wondering why the water behaves the way it does. Thank you for joining us on this journey through the subatomic. If you enjoyed this dive into the weird world of the very small, make sure to hit that like button. It helps us more than you know. Don't forget to subscribe to What Is so you don't miss our next video, where we'll tackle another of the universe's biggest, or maybe smallest, mysteries. If you have a topic you want us to break down, drop it in the comments below. Until next time, keep asking why, and maybe don't peek inside any boxes with cats in them, just to be safe. See you next time.